Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at a concept in radioactivity, and that basically lies under the broader concept of radiation and radioactive chemistry. So in that case, of course, we are going to look at how we can be able to represent the rate of decay. Now that we said that radiation is a spontaneous process whereby we cannot be able to define or determine which nuclei is disintegrating or which one is not, or the order of preference. So in that case, the decay rate is going to assist us to how to measure the number of decays per unit time. And this is where the concept of decay, of course, the radioactive decay stems from. So for that case, thank you and welcome. So our topic of discussion for today is going to be the way in which we can be able to represent radioactive decay. And that basically entails the kinetics of symbol radioactive decay. So this is in an essence, this is a decay. This in an essence is a simpler way of trying to find out how the radioactive decay process happens. Maybe in trying to, of course, try to quantify the decay rate of a radioactive substance. Now, this one comes from the fact that, as I've said, when we were trying to introduce the actual concept of radioactivity, we said that one cannot pinpoint which kind of nuclei or nucleus is going to disintegrate. Therefore, since it is difficult to determine this aspect or which specific atom will be the next to decay, we will use the concept of decay rate, which is actually denoted as A. So as we've said, from our mathematical interpretation of the term rate, this basically is the ratio between specific quantities. So in that case, if we were trying to talk about the concept of decay rate, then we can be able to define decay rate as the rate of integrations per unit time. And therefore, we are going to see different ways in which we can be able to measure this concept of decay rate or how it can be represented. So this is a measure of the number of disintegrations unit time. Of course, in this case here, we're going to see that time can vary, but the standard unit for time is seconds. But maybe in this case, we can be able to use a reference for days, years, etc. So this decay rate, as we have said, is a ratio. So therefore, when we are trying to measure it, decay rate is given as A. Or maybe I've just written it down here, so there's no need of repeating. So decay rate is given as A. So therefore, when we are trying to quantify it, we have stated that it's a quantity which can be given as the number of integrations per unit time. Now I've used this negative notation here intentionally because this process of decay rate, of course, when we are talking about numbers, this process decreases with time. So therefore, we are going to use a negative connotation to show that decrease. And when we're trying to represent this particular kinds of decay in terms of graphs, of course, we are going to see that we're going to use a particular set of exponential curves, which of course are going to exploit the concept of this symbol, which is of course in mathematical terms is a mathematical constant. I've basically introduced this here, or intentionally tried to introduce this concept because this particular discussion that we're going to talk about, the rate of disintegrations per unit time, is going to be some of the laws which we are going to state, which stems from the concept of logarithms. Now in that case, I've introduced this natural mathematical constant here because it is a base that refers to natural logarithms that is used in especially concepts that are relating to exponential growth or decay, in this case for the case of radioactive materials. So in this case, I'm going to just illustrate what basically this one entails in a recap so that you can be able to use it appropriately. So as I've said, the concept of this letter E basically is a mathematical constant. This is a mathematical constant that of course is a base of natural logarithms and is used in expressing trends that have got a decay or growth, exponential decay or growth. So if we have a function like y equals ex, where e is the number that we have defined, we're going to have of course the graph of x against that function appearing as such. So this is the kind of graphs that we call exponential curves. In that case, of course, bearing in mind that we understand the concept of exponents from levels of logarithms and indices. So in this case, for decay, which the rate of decay which occurs this order in a way that we are going to have a negative exponential growth or exponential decay, and we're going to have this one move in this specific order for that exponential curve. So therefore, if we have a function like x, or maybe a variable x, that we're going to use that natural log. So a number x to the log of a log to base of a number x can be represented as a natural log of x. So therefore, if you encounter an exponential equation or function that is having this particular kind of nature, then we're going to express it in an appropriate way. So in this case, if I just rewrite this, I can say the log to base e of y, function y can be written as x, and this is implying e raised to power x is equals y. Now looking at the relationship between these two equations, therefore we can say that the natural log of y is equals x. Now in this case, we are also going to find that there's specific rules. For instance, we know that maybe from indices, the loss of indices, a number b raised to power 0 is equivalent to 1. Now in that respect, for the natural log of a number e, it will always be equivalent to 1. So having reminded ourselves of those basic laws of those exponential expressions, or just the logarithmic expressions which are expressed in terms of a natural number e, we're going to look at what this decay activity or decay rate and the decay process basically entails, and try to figure out how we can be able to quantify different aspects of this decay rate. So in radioactive, the process of radioactive decay is referred to as activity. Radioactive decay, we refer it to as an activity of a radioactive source, which basically implies the number of decays which occur per unit time. And this one basically we are given as a decay rate, and it's measured, this particular quantity is measured in decays per second in units that are referred to as becquerels. We saw the significance of Henry becquerel when we were talking about the concept of radioactivity and how it played a role in trying to figure out the characteristics of these radioactive materials. And in this case, the units that are given, for instance, 1 becquerel is equivalent to 1 decay per second. So those are the basic units that are used to refer to the activity of radioactive or radioisotopes. So therefore, the activity of a radioactive source decreases over time as I had given using this exponential decay curve that I had given. So therefore, that one is understood and understood. The half-life of an isotope, which we are going to see now, when this particular quantity for a radioactive isotope disintegrates, there comes a time whereby the quantity which has been attained is half the quantity, the original quantity. Now the time taken between the original quantity and the quantity that has been attained, which is half the original quantity, is referred to as half-life. So therefore, this is another term. Apart from the term activity, there's another term that we can use to express the radioactive decay, which is known as half-life. And this one implies the time taken half-life refers to the time taken for half just write half the nuclei to decay basically it can just simply be that the time taken for half the nuclei to decay, or half the quantity of the nuclei to decay, or the time taken for the activity now that we refer to as the rate of disintegrations to move to half of the specific quantity that we have mentioned. Now, of course, it's this concept of half-life is characteristic in a way for that for different radioactive isotopes. Each isotope has got a characteristic aspect of half-life, and of course, it's constant and does not depend on the number of nuclei that have decayed. So therefore, half-life can be able to be determined independently in different ways, and as we have said, isotopes of different radioactive isotopes have got different types of half-lives. So in this case, as we have defined the term decay rate, half-lives, and we have tried to give a specific representation for decay rate, which was A equals the number of nuclei divided by the time. That's the ratio between the two. We're going to see a mathematical representation of the rest of the process of decay, which you have of course mentioned some of the areas that we were going to exploit in trying to explain it. So if I try to do an illustration using that, we have said that activity can be defined using that specific concept, whereby A, which is activity, is directly proportional to the number of nuclei present at that specific time. For instance, if maybe we talked about Avogadro's constant, therefore we can just use this. Suppose we have this number of atoms present at a specific time, and they show a decay rate of 5 atoms per second. So the decay rate of 5 atoms per second. Therefore, directly we can see the implication from this is that if we try to increase the exponent for this number of atoms by a factor of 10, therefore this is going to imply that this is going to change to 50 atoms per second. So the relationship that I want us to see is that these two particular aspects, the effect of these two particular aspects on the rate of decay. Now comparing this rate of decay and this one and the number of atoms present, we can try to just infer try to see the relationship between the two, and this is going to assist us in trying to figure out how this decay rate can be able to be mathematically represented. So if I proceed from that point, we have that one given as that, and therefore we can write from the first equation that activity is equals m over t, which is kn. So k in this case will represent a constant, and therefore we can be able to rewrite this equation using the two parts of our equation and eliminating that one. So we can write this one as with respect to time, negative kn, and as I said, the negative value represents that this is decreasing with time. So therefore, if we try to integrate this one, we will find the natural log of n with respect to t is equals negative kt plus c. So in this case, if we try to draw the graph of the negative n with respect to n against this t, we're going to have a straight line with a constant, which is a constant integration constant that we're going to have there. But our main interest for now is just to try and find out how we can be able to represent other aspects of this radioactive decay. So we proceed with that, and then we find that this one can still be represented as nt equals the natural log of kt plus c. So from the laws of indices, this still can be represented as, so for addition and the subtraction, of course, and division from the laws of logarithms, we can see that that is the concept that is being applied there. So therefore, this one can be represented as that one. So if the number of the nuclei present at some original time is given as t, and then maybe at a particular time, let's say the time is 0, the number of disintegrations can be given as n0, which is of course 0. Therefore, we can say that for a factor that is here, or for a start of the activity at t is equals to 0, we can give the number of disintegration from this particular formula by just doing a substitution, whereby we'll find that it is n, the t is 0, so therefore it's going to be n0 equals e negative k0 ec. So if we try to look at that formula, of course, from the laws of indices, still we can infer that this is n at t is equals 0, n number raised to 0 is equals 1 ec. So therefore implying that at t is equals 0, the number of disintegrations is equals that particular value. So at the time t is equals, of course, t, or maybe a specific value t, which is basically a value greater than 0, then we're going to have the number of disintegrations represented as nt is equals n naught e kt. So this is basically also represent, you can just do a rewrite this particular equation in terms of natural logarithms. We can write it and say that this one is equivalent to n over n naught, which is going to give us the product of a constant at that time. So therefore, we said that activity is directly proportional to the number of nuclei that are present. Therefore, from this formula, we can be able to also define activity by doing a substitution for activity instead of the number of nuclei. So therefore, we can say that implying A is equals A naught. So the rate of activity can as well be calculated from that concept. So if we try to convert this into a natural logarithm like the one that we have done before, so I'm going to do away with this so that we can be able to use this middle part. So therefore, from this, we can be able to write it in terms of this. I'm saying the natural logarithm of A over A naught is equals negative kt. Now that the number of disintegrations is equivalent, or the rate of decay is equivalent to the number of nuclei present. So since half-life for n is equals a half the number of original nuclei that were present, then that one means from this formula at a particular time or at half-life we shall have the number of nuclei that are present, which is going to be given as n naught E negative kt. From this we can see that these values are the same, so we can do away with them. And then we have a half is equals E negative kt. So taking logarithms on both sides, we know that for this natural logarithm that I've indicated as E, made from the laws of logarithms, the natural logarithm as I've indicated for E, if we are given a natural logarithm of E, of course, which is given as that, and this one is going to be P. So therefore, if we have the natural logarithm of kt, this is going to give us negative kt. So that is basically the concept that we are trying to imply here. So our next step is going to use that concept. So in this case, if we try to find the natural logarithm for both sides, we're going to have the natural logarithm of half is equals the natural logarithm of A negative kt. So in that case, we're going to have a natural logarithm of this can be written, remember 1 over x can be written as x negative 1. So therefore this is 2 negative 1, which is equivalent to the kt. This is negative kt. So this, since we have a negative and a negative there, so those values can be interchanged for a positive value, therefore implying that the t that we were talking about from this particular concept is half-life. So therefore t half-life is going to be represented as negative kt. This is not going to be negative since we have just eliminated that negative from this. There's a negative here from this exponent that is going to be. So this one and this other negative, just do away with them. So therefore, making t have the subject of the formula, we are going to have the natural log of 2 over k. This is natural log of 2 over k. So that value, we can be able to obtain it from our tables of logarithms. So therefore, that one will give us a formula for half-life for decay activity of a radioisotope, particular radioisotope, which is generally represented as half-life equals. So the value for that one, half-life, that numerator for the natural logarithm of 2 is that one, divided by the decay constant. So if you were given the decay constant for a particular radioisotope, then we can be able to calculate the half-life in that case. So these are some of the procedure that we have done step by step that is used to represent the kinetics of a simple radioactive decay. Now we're going to use a sample question in trying to find out how we can be able to quantify, given specific quantities, maybe the number of decays, the time, how the decay rate, how can we be able to find one of the factors that we have discussed. So let's try to look at one of the sample questions. So I'm going to read a question and then we just extract the information from there and try to use it to solve this particular figure. So in this case, we are told a sample of radon gas, radon is a radioactive isotope, a sample of radon gas, which is radon 222, a sample of radon gas has an initial alpha particle activity. So this is an activity of alpha particle initial. So I can just denote it as such, initial for this initial, but basically we should remember that this is an activity for alpha particle of 7.0 times 10 4 disintegrations per second. So this is an activity for alpha particle, the initial one. After 6.6 days, so the time t, 6.6 days, its activity A, now we have A naught and A, so the activity A is 2.1 times 10 raised to 4 disintegrations per second. So if we try to look at this information and then we are requested to find half-life of this particular radon gas. So therefore, I can just repeat the question for the sake of clarity. So a sample of radon gas, that is Ra222, has an initial alpha particle activity A naught of 7.0 times 10 raised to 4 disintegrations per second. After 6.6 days, its activity A is 2.1 times 10 raised to 4 disintegrations per second. Find T, which is the half-life of radon. So the approach that we're going to use for this is we have been given what we called rate of the disintegration, which is given as A. So therefore, we're going to use this formula that contains A naught KT. So this one we said can be written in the form of natural logarithms where the two rates of disintegration, which is going to give us KT. So therefore, this is the formula that we're going to use, the ratio of those disintegrations. And we're going to see that from the formula, we're going to have the natural logarithm over A naught, A, just A, not A naught, A, 10 for disintegrations divided by A naught. This is times 10 for disintegrations is equals negative K times 6.6 days. So since we have just used this formula, we're going to maintain that negative sign there for the values of the product on the right side. So this one for these powers, we're going to have them, and this is going to be the natural log over 3 is equals K times 6.6. So in this case, we're going first to find the constant, and therefore K is going to be 0.8. Just a minute. So given that T half is equals 0.693 divided by K, this is 1.8. So therefore this is going to be 0.18, and therefore T half-life is going to be 3.8. So we had used that one in forms of days, so it's going to be 3.8 days. So kindly confirm the calculations for this so that you can be able to comply with what we have already discussed. I'm assuming that what I've done here is accurate, but in case we find any correction for these calculations, we can be able to do it in the comment section. So for this case, of course, these are the concepts that we're going to use for finding out some of the arithmetic or the arithmetic forms of calculations given specific quantities all the time for this radioactive decay process. So that is it for today. I hope that we have understood this concept, simple kinetic procedures for which we can be able to use in obtaining the half-life, the rate of decay, and the decay constant for specific radioisotopes. So that's it for today. Thank you guys. Bye.